So in today's lecture, I'm going to talk a little bit about how we can create polarization and how we can manipulate it with waveplates and rotators. Do a couple examples, and then we'll move on to some considerations for interference. But there will be supplementary lectures to this one. Remember, in the last class, I mentioned that there are several sort of ancillary topics to polarization that I won't have time to cover in the lecture here. For example, things like how do you make a quad wave plate, or how do you make a really nice polarizer using birefringent materials. And there are also a couple other topics like optical activity, circular birefringence, etc., which I will also cover in the ancillary supplementary lecture. So watch for that. That should be posted fairly in the next 1 or 2 days. And if you have any questions, of course, bring them to me in the next class, or you can come talk to me anytime in my office. Okay, so let's start. First, let's talk about why so first, let's talk about, ignoring the equations for a second, let's talk about why sunlight is polarized. Okay, and this has to do with scattering, going back to an earlier topic that we discussed a few weeks ago. It has to do with the fact that when sunlight, which is unpolarized, comes in and hits a molecule or atom that is sitting at this point O over here, then it creates these dipole moments like we discussed. It causes the charges, the electrons in the atom to vibrate, kind of like a harmonic oscillator, like a driven harmonic oscillator, and that causes a dipole radiation. And it turns out dipole radiation, if you've studied it in other classes, then you'll know that it has a certain pattern. It basically looks like a little peanut. Okay, so there's like a peanut pattern which is oriented from this dipole, like a peanut, and then there's another pattern that's oriented along that dipole, like that. And precisely at 90 degrees with respect to the dipole, you'll see that the dipole does not radiate in that direction. Okay, so for example, that at 90 degrees to this, I guess it's along the axis. Sorry. So at exactly 90 degrees here, there is a perfect polarization, which is due to the dipole that's oriented in that direction, but the dipole that's along the same axis, as that as this direction, which is this dipole moment, does not have any component in this direction. Similarly, in the direction of the Z over here, the all of the polarization or all of the electric field is parallel to this dipole moment, but is that the dipole which is point along that axis, along the Z axis, does not have a component in the Z direction. Okay. And so we can, and at some arbitrary point, of course, there's going to be both components. So it's going to have some general polarization. So you can see there are certain specific directions in which the sunlight will be perfectly polarized. And also in some arbitrary direction, there'll be some kind of linear polarization, but it won't be exactly along those axes. In fact, it'll be elliptical because of phase differences and things like that. And of course, in the forward direction, they both end up scattering, and you get perfect, and you get unpolarized light in the forward direction. These are just some formulas. They're not super important, but they just kind of tell you again that, you drive the charge, R is a coordinate. Let's say this is a very classical picture, obviously not really what's going on in a quantum phenomena, but it again gives us some intuition for what's happening. So we have the dipole, the position of the electron is driven, is assumed to be vibrating, oscillating at the same frequency as the incident electric field. And so then we expect that will respond like a harmonic oscillator in that Lorentz model that I've told you about before when it comes to scattering. And then the scattered light, it turns out, is proportional to the derivative, the second derivative, that is the acceleration of the charge. Okay, this is coming from a basic result in electromagnetic theory. Okay, and so that scattered light is proportional to the or the electric field is proportional to the acceleration, and the intensity, of course, we know is proportional to the square of that electric field. And so substituting all that in, we get this scattered light then goes as omega to the fourth, which is again the Rayleigh scattering. Remember, we argued that Rayleigh scattering will have this dependence of omega to the fourth, or 1 over lambda to the fourth, because omega is proportional to 1 over lambda. So therefore, we have recovered sort of that same idea by understanding now the exact mechanism, which is the scattering of a driven harmonic oscillator. Okay, so this is why sunlight might be polarized. And so we take advantage of this fact that the sunlight, when it is coming down, this may be predominantly, this light that is scattering off of a horizontal surface, such as a road or a ocean, etc. That is going to be predominantly in the horizontal vibration. Meaning, so if I were to sketch it, or maybe I should just try to show it. So let's say that I am looking at the ocean, okay? And so picturize that, here's the ocean, and you're all looking at this ocean. And then the light that makes it through, of course, comes off of the ocean, right? And when it hits the surface of this ocean, let's say at about Brewster angle, then the light is going to be predominantly polarized vertical to that plane of incidence. Remember, the plane of incidence is now vertical, and therefore we're going to have light that's predominantly polarized horizontally. Okay, so it's going to come into your eyes more horizontally polarized than vertical polarized. So what we do is we take advantage of that by taking sunglasses, and we orient the transmission axis of the Polaroid film in the sunglass at vertical to reduce the glare of that horizontally polarized light that's coming off the ocean surface, water, roadways, etc. Okay, so this is just one example of how we take advantage of this. Other types of polarizers that we can create. So you've done in your class now, you've seen that, sunlight, any unpolarized light that hits a piece of glass has, at the Brewster angle, is predominantly polarized, at that vertical polarization or S-polarized light. And then the transmitted light is predominantly now horizontally polarized. So what we can do to increase the sort of the degree of polarization is take many such plates of glass and stack them together. Okay. So suppose we have that the transmitted light, as we know, has some S polarization fraction, which I label as T perpendicular, which we can calculate from the Fresnel coefficients. Okay. So you take the Fresnel coefficients at the Brewster angle, and which we have already shown in several graphs earlier in the class. We find that the transmitted light has a polarization fraction. Now this is the intensity. Remember, this is the power transmission coefficient or the transmittance that I'm writing here, which is T perpendicular, capital T perpendicular, and that's about 0.8 out of the incident intensity. Okay, I perpendicular, and the transmitted light, of course, has parallel polarization I parallel. Okay. So for n plates, as you can imagine, I just keep multiplying these perpendicular T perpendicular intensity, and each time I'm going to get this T perpendicular to the power 2n I perpendicular. Okay, and therefore I will get that the percentage of the polarization in the transmitted beam is 1 minus this fraction over here, which I'm just calculating by just taking the total S polarization intensity and then divide by the I parallel. The parallel, there's a little bit of the parallel light, that fraction, plus the amount that's in the perpendicular polarization that is being transmitted as well. And so this way, as you can see, because T perpendicular is 0.8, this guy here, as I increase the number of plates, is going to keep increasing rapidly. Okay, decreasing rapidly. Okay, so by the time I get to n, which is few, this fraction over here is very small, right? It's almost 0, let's say. Then we just get 1 approximately. So the polarization of the light that's going through becomes nearly perfect parallel. Okay, and and of course I should note that 2 comes from that there are 2 surfaces to the beam, and we can show that the polarization that T transmittance is the same at both incident and the other surface. Okay, so this is how we can build a better polarizer simply based on the polarization by reflection lab experiment. So now I want to talk about phase retarders or waveplates, because this is another thing that you've seen in your lab experiment. Okay, let's see. Hide that, but it's fine. So in this situation, what we have done is, again, we have taken, say, unpolarized light, which is coming in, and we have got a wave plate, which, as I mentioned to you, in a wave plate, we have something called a fast axis and we have a slow axis. And the idea of the fast axis is that light that's polarized along the fast axis, meaning the direction of the polarization is along this axis, fast axis, is transmitted with no change to its amplitude, but it is given an extra kick, a velocity, basically, meaning the velocity of this wave through the material is faster than the other component, which is along what we call the slow axis. Okay, so the light arrives sort of earlier, if you like, at the location on this axis versus this axis. Okay, and if I write down, say, the expression for the velocities, right, and here what I've done is simply taken the fact that right after the plate, okay, what is the phase of each of these components? Well, it's cosine kz minus omega t, right, for each fast and slow axis. So for the slow axis, kz minus omega t, which is now I replace z by d because that's the thickness of the plate. Right after this plate of thickness d, the cosine k d, I put t equal to 0 here just to make it simple. We don't need all the extra factors for a minute. So what this does is, and the k, which is the wavelength of the or it's a wave number, the angular wave number of the light, angular spatial frequency, etc., that is just given by 2 pi over lambda. And lambda is simply the velocity of the light, which is v sub s for the slow axis, divided by frequency. So the frequency goes on the numerator over here. Same thing for the fast axis over here. Okay, and with some manipulations, you can show. Okay, with some manipulation, you can show that effectively you could imagine taking this out and factorizing it, if you like, or writing this in terms of the difference between VF and VS, and then you'll find that you can factorize out that term. There's also another easier way to do that with phasors, but I won't get into that today. So the point is, at the end of the day, that let's say that the E0x component has this term, and then the E, and of course, now let's add back cosine omega t into it. Let time evolve from t equal to 0. This will have cosine omega t, and this will have or cosine kz minus omega t, and this will have the same thing but with this extra factor, 2 pi f nf minus nsd over c. Okay, so, and you'll notice that because the velocity of the fast axis is faster, remember the velocity and the refractive index are in inverse proportion to each other, which means that nf is going to be lesser than ns. So this term here is, generally speaking, for the fast axis, I mean, this phase difference is going to be negative if nf minus ns is positive. Okay, so or sorry, if the velocity of the fast axis is indeed faster than the slow axis, this term is usually negative. Okay, so this is always going to essentially, do you remember that when epsilon is greater than 0, then the y-axis will lead or lag behind the x-axis? When this phase difference is greater than 0, call this epsilon or delta phi, the phase difference between the y and the x. If this part is greater than 0, then the y component leads or lags the x component. It may help to put back the omega t component to see that. So what happens if I add in back minus omega t here and cosine kz minus omega t here? Anybody? Then will the y component lead or lag if epsilon is greater than 0? No idea. People are confused. Yes. Exactly. Very good. And so if you didn't follow that, what she's saying is, I have the x component, x hat, as cosine some term kz minus omega t, which is the general term, okay, plus the y component. I'm ignoring all the factors in front. Cosine kz minus omega t plus epsilon, right? Where this epsilon or delta phi, all I might use all of these terms is this 2 pi over lambda. And now I'm just going to write down what it is, nf minus ns times d after the wavelet. Okay. So if epsilon is greater than 0, okay, then this term here, okay, because of the minus sign in the omega t term, it requires some more time t to catch up to that term, right? Okay. Or another way to say that is if I write this as minus omega t minus epsilon over omega, basically I'm just taking this term and just pulling out the omega. I need to wait an extra time, epsilon over omega, for this term and that term to catch up. Or as she said, because the cosine will be at a maximum first compared to this term over here. Okay, because there's a relative minus sign between them. Okay, so that's what you should always remember. Even if you can't remember off the top of your head, you should remember how to reason it out in this way. Clear that? Any questions? How to think about that? And by the way, this number n times d, okay, so ignoring all these factors, these are just constants, right? For a given frequency of a optical wave, a frequency of visible light or a laser, etc., frequency is just fixed. Okay, so it's 2 pi f over c, is just some constant. This constant is of course important. It's 2 pi over the wavelength, lambda naught. Okay. But then n times d for the fast and minus n times d for the slow, this n times d, this factor, you saw this earlier in Fermat's principle. We call that the optical path length. Okay, so the optical path length is always the refractive index times the actual geometric length. So here the thickness of the plate was d, so the refractive index times that d is called the optical path length versus the geometrical path length. So this is the optical path difference, because it's the difference between the two fast and slow axes when you go through that plate. Okay, so that is the path difference. So what we have here, this expression here, is equivalent to 2 pi over lambda naught. As I said, f over c is just 1 over lambda naught times this nf minus ns. Usually when we're just talking about the phase difference and we don't worry about the sign just yet for a second, we don't worry about the sign. Okay, but let's say that if delta phi, normally NF is going to be lesser than NS because VF is greater than VS, then this term, this sign of this will be always less than 0. Okay, if it's greater than 0, then we know what happens. If it's less than 0, we know the opposite, that EY now must be leading EX. Okay, all right, and but for the magnitude, we can see what the magnitude is. We can just find that, and by making the thickness of this plate a certain amount, taking the difference between this, multiplying this, if we set that equal to lambda over 2, okay, if I set all of this, the optical path difference, if I set that equal to lambda over 2, so now I can calculate what thickness I must have, given the fast axis and slow axis refractive indices, which are just the component properties of whatever material that I'm using, okay? So NF and NS could be given, right? You will find the difference times D, the thickness of the plate, will be set equal to lambda over 2. As soon as that's true, then delta phi will become pi over 2. Okay. Sorry, lambda over 4. That's a quarter wave plate. Okay. So this is lambda over 4 will give me delta phi equals pi over 2. And pi over 2 is special because we have talked about for circular polarized light, we need a phase difference of pi over 2. Okay. So this is a quarter wave plate put in the path of a linearly polarized light will end up giving us circularly polarized light. Because of this relationship that the quarter wave means just that the optical path difference between the fast and the slow axis is lambda over 4. Okay, that gives me a phase difference of pi over 2. Okay. Similarly, for a half wave plate, again, just replace this product, the optical path difference, by lambda over 2. That's a half wave, okay? And when I put lambda over 2, then I'm going to get basically pi, right? And so these are the two possibilities that we work with initially, and those are typically all you need in most of the simpler experiments that we're doing. And now we can see also that a pi over 2 wave plate, quarter wave plate will give rise to either circular polarized light, if we put it at exactly 45 degrees to incident, linearly polarized light. That's because the two components will be equal, because it's 45 degrees with respect to the axis, and with respect to the fast or slow axis, which means that the components on the fast and slow axis are equal. And now the phase difference is pi over 2. Okay. If we have in general for regular fast and slow axes, we'll have that this term is negative, so we're going to get right circular polarized light, because whenever EY is lagging behind EX, that's when we get right circular. When EY leads EX, we get the left circular polarized light. Okay. Okay, and so what about the pi phase, that is the half wave plate? Okay, so I've told you now with the quarter wave plate, I can create a circular polarized light, either left or right. Okay, and the other option is and we can simply change whether we're doing left or right by, for example, flipping the angle of the linear polarized light. So, for example, from 45 degrees, if we make it minus 45 degrees, we're going to get the other right circular polarization from left, or whichever way you're thinking about it. Okay, because that just puts a minus sign in front of this guy. Okay. Yeah. So the last part that you need to think about is for the half wave plate. What does a half wave plate do to linear polarized light? Okay. Again, we can think about this by considering what happens to linear polarized light when it enters into this system. Then again, if we go back to this expression, basically, if I put a pi here, that just means I'm flipping the sign of the y component, right? Because cosine of pi is minus 1. Okay. So that means that whatever incident, if the incident light is polarized at some angle, okay. Oh, one more thing. For the quarter wave plate, if I came in with an angle that wasn't 45 degrees, what will I get coming out from the quarter wave plate? I talked about if it's exactly equal, you'll get circular polarized, either right or left. What happens if I'm off of 45 degrees? Yes, elliptical, exactly. So you can produce elliptically polarized light as well. Okay. And so for the half wave plate now, if this component is now a minus 1, which means I just flip the sign of the y component from whatever the incident light was, I just flip the sign of the y component. So if the incident light was linearly polarized in the first and the third quadrant, meaning if it was lying like sort of in this direction over here, okay, I flip the sign of this guy, okay, the y component. So now it's going to lie in the second and fourth quadrant. Okay, it's like rotating it by by 2 theta now, because initially, let's say if the angle of the polarization was alpha, now it's going to be lying at minus alpha with respect to the x-axis. Okay, which means that it has rotated by an angle 2 alpha. So that's another general fact to remember, which is easy, hopefully, to remember, which is that the polarization state, if it is making an angle alpha with respect to the fast axis of the half wave plate, will rotate by the angle 2 alpha. But you don't need to remember it, as long as you can remember that it flips the y component. Then you can rederive that on your own. Okay, and I've just said that here. So it just now it flips that. So this is how we can build a rotator for the polarization state. So if I come in with linear polarized light along, say, the x-axis, and I want to produce 45-degree polarized light, okay, then what I can do is put a half wave plate at an angle of, if I want to make it go from, say, x polarized to 45-degree polarized, what should be the angle of the half wave plate? The fast axis of the half wave plate should be at -45. Maybe? Yes.
22 and a half.
22 and a half. which I just said, which is that you have to take the components and you flip the y-axis, which means it's equivalent to rotating the polarization state by 2 times that angle between the fast and the axis and the polarization. Maybe not clear? Yeah. Okay. So if this is the incident light, and let's say that the fast axis of this, I'm sketching the fast axis and the slow axis like this. The incident light is over here. So this is E. Maybe I should use some. Let me use these thicker arrows to denote the direction of the axis. Okay. So this is the fast axis, F. If this angle is alpha, okay, then I'm saying that the component along this axis flips, right? From being positive to being negative. Okay. So that means that this outgoing light now will be at the same angle alpha. Okay. Sorry. So yeah, the outgoing light will, I sketched it along the slow axis. Sorry, one second. It is that. Okay, I sketched it along the fast axis. Ignore the slow axis for a second. You can picture that there's a slow axis that's at 90 degrees with respect to the fast axis. Okay. So what I'm saying is that now the component along the slow axis remains the same, but the component along the fast axis flips by 180 degrees or by to the negative side. So which means that I can generally write that. Basically, it's maintaining the component along the S, the slow axis, but it is now, it's going to have an opposite sign on the fast axis. Okay, so the total angle now, right, which it has rotated by is 2 times alpha. Basically. Okay. So if I start with the original vertical polarized, if I start with the axis at 22.5, it will rotate it by 45 degrees. So initial X polarized light will turn into 45 degree polarized. Or if I want to go from X to Y polarized, I'll take the angle of the halfway plate at 45 degrees. Okay. Okay, let's do another example. Maybe this will help. And I think you all should try this example to your friend, and then we'll talk. Okay. So vertical polarized light is incident on a quarter wave plate. This is the type of problem you'll see on the exam and things like that. So let's try to work through one of these. Whose fast axis is at an angle 37 degrees to the vertical. Okay. Write down the X and Y components of the field after the quarter wave plate. What state of polarization is this? Okay. So is that clear? Is the statement of the problem clear? The fast axis is at 37 degrees to the vertical, and the incident light is vertically polarized light. One, I'll make even a sketch for you so that you know. Yeah. Here's our polarizer. Quarter wave lecture. 37. Here's the laser beam. Incidentally, it's vertical. Let's call that the y-axis. That's the y-axis. So that's the x-axis. And we have the fast axis of this. I'll give the dashed lines here. is at an angle 37 degrees with respect to the vertical. What is the output polarization state?
It's gonna come out. Yes. There's one of the slowest part along. I'm sure that the fast
Yeah.
by 74 degrees.
But it's all that matters is the relative phase between fast and slow. Only fast.
The slow part. The in lag 74 degrees.
So you're saying it's 74 degrees because it's a quarter wavelength, not a half wavelength. Let's make sure you know that. So it doesn't produce a pi fish. It produces a pi over 2 fish.
Yeah.
Right.
So it's still yeah.
Oh, you maybe it's still there.
We are.
Okay.
Last month's game or last actual game was fun to watch and somebody loves to watch. I'm excited to watch.
But I'm pleased with it. The right or left? 10 degrees. This is the only sense of the owner.
Yeah.
Remember, the fast axis will give you a negative sign on the phase difference between the components. So because the fast is a higher speed but lower refractive index, so the phase difference is negative. If it's pi over 2, it will be a negative. So it's 37. So sorry, I mean keep discussing if you like, but kind of had to move on. But so does anyone want to suggest what? Let's approach the answer by stages. Do we think we know kind of the type of light that is going to come up? Whether it's going to be, let's say, you've seen several choices, right? It's linear polarized, circular polarized, elliptic polarized, and unpolarized. These are sort of broadly the 4 types of states of light that I've told you about. Which of these 4 do you folks think would be the state of light coming out? Yes, Jack.
Elliptically polarized.
Elliptically polarized. And why do you say that?
Because it's not at an angle of 45 degrees.
Right. Exactly. Very good. Because the angle of the polarizer with respect polarization with respect to the fast axis is not 45 degrees. In 45 degrees, the components along the fast and slow axis would be equal to each other. Or if it was 90 degrees, then of course the light will be entirely along the fast axis or entirely along the slow. Oh, by the way, that's an important case to know about also. I should mention that. So what happens to vertically polarized light when I send it with the angle to the fast axis as exactly 0 degrees? What would I get out? Yes?
It just stays linear.
It stays linear, exactly. Because there's nothing to compare it to, right? Same thing with like slow. Like if I oriented slow as well to the vertical, it would also remain vertical. Okay. So nothing happens to linearly polarized light going through a quarter wave plate or half wave plate, as long as the angle is 0 degrees between the axes, okay? Or 90, because that means it's lined up with the slow axis. Okay? But yeah, as you all have pointed out, if it's at 45 degrees, then the two components are equal, so we would get circular polarized, but we don't know. Here we clearly see it's not circular. It's going to be 37 degrees. So you can calculate the angle, the cosine and the sine to get the components of that. Okay. But now let's come to of course, the tricky part. Okay, right? Which is, what is the handedness of this elliptical polarization? Is it going to be right elliptical or left elliptical polarization? Does anybody think they can understand the answer to that? Suppose it was at 45 degrees. Then what would you say? Forgetting about right or left, right? Because the handedness doesn't matter what the angle is exactly, right? If it's 45, if it's 35, it doesn't affect the handedness because that just depends on the phase difference between the left and the right, between the fast and the slow axis.
Rotating clockwise, looking into the beam.
Why do you say that?
Because if you draw the fast and slow axis, you make a projection.
Fast and slow axes, which are shown here. So this is
They are 90
this is slow, this is fast. Okay.
90 degrees to each other. But
Yeah.
then you can imagine the resulting beam as two beams that are 90 degrees of each other. And the slow axis will lag behind. So it's like that.
So it turns this way, looking into the beam, like that.
Yes.
So it will be to the left.
Oh wait.
That will be left.
Clockwise.
You think it's clockwise now? That way. So right circular or right elliptical, right? That's what you're saying. Everyone agree with that? Right? Yeah. I believe it is right also. I could be wrong. I've been known to get this one wrong too. So you're not the only one. So the other thing I should point out is another way to think about it if you're a little bit confused, because in this one, what's slightly different is that the fast axis is rotated and the polarizer is said to be the same. Whereas the cases we have considered so far, the fast axis is usually vertical, let's say, and it's the angle of polarization that has been rotated. Okay. And of course, there's a symmetry between those two situations. So you can argue that if I just rotated everything to the left, up to that situation where it was, this was the fast axis, this was the slow axis, and then I'd have to rotate the vertically polarized light by that amount, or the same amount, to preserve the relative orientation between those situations. Okay, and now we can argue about the angles. Okay, the angles, just means that this one is positive, right? Fast axis positive, slow axis is now negative, that component, along that component. And also gives me then the minus pi over 2, so it's going to end up rotating to this side, towards this way. Oh, wait, that would be. That would then be left. That would be then left polarized. No? Right. Yes. Sorry. Okay. So I got that. So the state of light in this situation is E x 0 is just E naught cosine theta. E y 0, yes, sine theta with a minus, where the theta is at 37 degrees. E y 0 is E naught cosine theta. Okay, and the state of the light then is E, the vector, is simply E naught cosine theta times plus AX minus omega T, AC, so omega T. That would be the Y component. And we know that after this goes through the fast axis, it's going to get a negative pi over 2 phase difference. So yeah, I mean, if you're ever lost, then this is the way to go. Plus x hat E naught minus x hat E naught sine theta cosine AZ. Okay, so we can now look at this at time t. So now looking at this at some point over here, which I'll call the origin just to make everything easy. So the electric field vector at that point is E naught cosine theta and cosine of minus omega t plus pi minus pi over 2. So that's going to go as there minus x hat E naught sine theta. Okay, so continuing in this fashion, just I know a little bit slow, but is guaranteed to give you the right answer. Okay? You can't go wrong with this. Is cosine omega t plus pi over 2 minus x hat P naught sine theta cosine omega. Okay, now we can talk about how this must be rotating if I were to look at it. Okay, so this term here is minus sine. So there's a minus sign, but that's unimportant because it just means that we just chose our time origin wrong. So we don't care about the overall minus sign. We just care about this effectively is y hat E naught sine theta sine omega t. As I said, I'm putting the minus sign outside and it doesn't affect the handedness of the polarization, plus x hat E naught sine theta cos omega. Okay, so at time t equal to 0, everything is going to be along the x-axis with the magnitude Ex0. Okay. And at some time t later, okay, this is going to rotate upward because the sine component is going to increase positively and the x component is going to decrease negatively, or it's going to decrease. So everything is going to go like that. Looking into the beam, therefore this is left circular or left elliptically polarized line. So we have Ex0 and Ex. Okay, so this is guaranteed to give you the right answer if you go through all these steps. I know it can be a little work, but it's preferable to guess it. Unless I made a sign mistake. Okay, so that's always possible. So, I wish I was better at this.
So you are saying that drawing.
Yeah, that's enough. Not right there. Yeah, what is wrong? Sorry.
That doesn't make sense if it went that way, looking into.
Why?
Can I draw there?
Yeah, sure. Come up and come.
Either this, like if I just imagine this to be the wavefront, it's going to be breaking into two components.
Yeah, very good.
But this one just travels at the same speed. This one is slower.
Right.
I can just imagine, okay, at some time this component is just going to stay here, but this component is going to.
Very good. Yeah. Right.
So I connect.
Very good. Excellent. That is true. Absolutely. And that is left circle. Oh, no. That's the mistake I made. I see. Yes. So what you drew is exactly correct. And maybe that's actually a nice way to think about the direction of the rotation. But the problem with this is spatial dependence, right? You're taking space point 1 and space point 2. Okay. Whereas the way we have talked about left and right circular, we have frozen the space point and progressed the time evolution. So when you go spatial, you must flip those two definitions, because if you think about spatial, to get a right-handed screw to turn, you would need to go that way. This is the right-handed screw going towards the observer. If I place my right hand along the direction between the source and the observer, right-handed polarization will screw the other way. So meaning this vector would have to turn in that direction. And a left-handed screw would turn in the direction that you just wrote. Because I'll put my left hand and turn it. I'll put my left hand between the source and the observer. That is left circular polarization. Does that make sense? Okay, we can talk about this after, because I'm out of time for the rest of the class. Okay. I had many other things planned for today. So this has to, what I was explaining to him has to do with the difference, if you like. We've been talking about freezing the spatial point at say kz equal to 0 and looking at the time evolution at that point. There's another way to think about the handedness of polarization, where you look at how the vector rotates as a function of space rather than time. So you freeze the time to say 0 and look at how the vector must be rotating as a function of space. Okay, so like he just drew, I freeze it there, and then the other guy has moved here, which is along this direction. I actually like this because it immediately tells you which way the vector is rotating, but you just have to understand that in that case, we have to argue on the basis of the handedness of a screw that's turning in the spatial direction. Okay, that's all I want to say about that, and we'll come back to it if you have more questions. I have only like 5 more minutes, but it's worth trying to finish some more because I'm so far ahead. If you bear with me, I'll try to get through some other stuff. Okay, here's another example. Okay, I'm going to go through this one fast because we've kind of talked about this quite a bit. So again, if I take a linear polarizer and I orient it at 45 degrees with respect to unpolarized light, the state of the light, the polarization of the light that's coming through is now 45 degrees in this axis. If I now put a quarter wave plate with the fast axis along this direction, then again, we'll get left circular polarized light coming out like this. This is very similar to what I just drew for the 37-degree orientation, except now it's 45 degrees. Okay. And so that's going to give me left. So I was actually right. This is another way to know that I was right. This is going to be left circular polarized. And then if I put now a quarter wave plate again, so now what happens? Now I have circular polarized light going through a quarter wave plate. Okay. So that might be a little tricky to understand, except that you can think of 2 quarter wave plates with nothing between them as a half wave plate, right? Because 2 quarter waves joined together is going to give me a half wave. So again, this is going to rotate the orientation by 90 degrees because it's twice the angle between the fast axis and the polarization. So it goes from 45 degrees this to that 45 degrees. And now if I put a linear polarizer, the only time it will pass the light through is when it's exactly in this orientation, okay, which is crossed with respect to the original orientation. And so if I put it back at the same, if I put this linear polarizer initially along the same axis as this one, and I put a quarter wave plate, these 2 quarter wave plates in between, I'll get 0. Okay. So this is a polarization analyzer for circular polarization. Because I've created left circular polarized light, which will get transmitted as this linear polarized light. But if I send in if I send in the other polarization, then I will get nothing. So we can use A plus B essentially as a circular polarizer, and then we call the CD combination as a circular analyzer, similar to how we did polarizer and analyzer combinations with just linear polarizers. So we can create circular polarizers. Sorry. So this is an example of how to analyze not just linear polarizations, but also circular polarizations. Okay. Okay, so that brings me to sort of the conclusion of the polarization part of the class. I hope to get started on interference today because that's your lab experiment, but because of the time we spent on the examples, but I think that's helpful because spending time on examples, I think, helps you to clarify, issues and conceptual understandings. So I think it's okay. Even though I'm behind, hopefully we can catch up a little bit in the next class with interference. All right, so I'll just stop, and please remember to watch out for those other videos on supplementary videos on birefringence and optical activity and so on. Okay. All right, I'll stop here.